Hi there. In this video we're going to be looking at a two-source DC resistive network. I have one drawn here. I have a battery which we call V1, 52 volts, another battery V2 which is 8 volts. We've got a 4K resistor here, one here, a 3K resistor up here, and a 1K resistor on the end here, and terminals A and B. And what we'd like to do as a task is determine the voltage between A and B using the superposition theorem. Okay, so we're going to determine VAB using superposition. So we've got two DC voltage sources here, and what we need to be able to do is to determine the contribution from V1 on the left here solely. That means replacing V2 with a short and then determine the voltage between A and B solely contributed by V1. Then we will replace V1 with a short and put V2 back in, and we will determine a contribution then from V2. Then we're going to add that contribution from A and B, from V1 and V2, add them together and superpose those two figures, and we should arrive at the actual voltage between VA and B. And of course afterwards, when we've been through the theory, we'll have a look at producing the same results on the simulator. Okay, so let's have a look first of all then at source V1 only. Okay, so a quick sketch of what that circuit would look like. Here we go, V1, 52 volts, there's a 4K, there's a 4K, no battery here, we're not considering V2 at all, and of course we've got the rest of the circuit over that way. There's B, 3K here, that's a 4K, and that's a 4K resistor also. Okay, now then, we've also got resistor here, which is 1K. What we'd like to be able to do is to determine this current here, IL. Okay, we consider this 1K resistor as a load resistor, but this is only a current contributed by source V1. So that subscript 1 there, we can denote by a superscript dash, so a single dash there, so IL dash. Okay, that's come from V1. Later on we'll have a look at IL double dash, and then we're going to add IL dash and IL double dash together. That's going to give us our target answer. Okay, what we also have coming out of V1 is a current here, which I can denote by I1 single dash meaning the 1. Okay, so 1 dash for V1, 2 dashes for V2, etc., as we'll do shortly. Right, now to be able to start a solution to this problem, what we need to know is what's the resistance that battery V1 actually sees in this particular configuration. Well, let's call this, shall we, let's go for a different color. Let's have a look at RT. So the total resistance, RT, contributed by source battery, if you like, number 1. And that is going to be equal to, well, we travel this way from V1, you're going to see this 4K resistor. Okay, so 4K comes in, plus, and then we're coming along here, you can go that away or that away. Okay, if you go to the right here, then you're looking at, well, you're going to journey through a 3K and a 1K, which is 4, and that is in parallel with this 4 here. Okay, so it's going to be 4K times 4K. So these are in parallel, so it's product over sum. 4K plus 4K. And that, of course, is going to be equal to, well, 4K plus 4K times 4K gives you 16 million. 4K plus 4K gives you 8,000. 16 over 8 gives you 2. A million over 1,000 gives you a K. So that's 2K altogether added to the 4. So a total of 6 kiloohms. That is our value for RT dash. So in terms of the current which emerges from the battery, this thing here, I1 dash is equal to the battery voltage itself, which is 52, divided by the resistance which the battery actually sees, which we've just determined to be 6K. Okay, and work that one out. Of course, we're going to have 8.666 recurring. So recurring, we put a dot over the 6 milliamps. Great. Okay, so what we've decided is that we've now got a current flowing down this leg here, which is 8.6 milliamps. And that is going to be shared that way and that way. Now you can see some symmetry here. There's a 4K down the middle branch here vertically, and there's a 3K and a 1K. These two. Add them together because they're effectively in series over there. So we use current division, and we can say, okay, let's just write that in. Current division gives us IL dash is equal to, that's supply current towards the branch there, which is 8.6 recurring milliamps, multiplied by, and then for current division, what you do is you say, I want to know the current going along the top here, this branch down there. So I need to multiply by the other resistor, that one, and divide by the total resistance in the two paths, which is, of course, 8K. Okay, so again, we're going to have some cancellation here. The K and the K will cancel. The 4 over the 8 gives you a half, and half of 8.6 recurring milliamps is going to give us 4.3 recurring milliamps, and it flows downwards. Okay, so yeah, 4.3 milliamps flows down through the 1K resistor. Okay, so that's halfway through the problem. What we'd now like to be able to do is to determine the current flowing through the 1K resistor solely produced via V2, the second battery source. Okay, so source V2 only. So source V2 only. Little sketch of what the circuit looks like. Over here we've got a short on the battery now, so we've taken the battery away, replaced it with a short, or link if you like, going across to A and B. Here's A, here's B. That's a 1K, that's a 3K. Here we've got 4K, and below that we have V2, which is our battery, and it's 8 volts. There's a 4K here, that was 4K. Right, and what we'd like to be able to do is to say this thing here is now going to be current through the load resistor due to the second battery, V2. Okay, so IL double dash. Right. What we also have is a current emerging from the battery V2, which we shall call, well, why not call it I2 double dash. Okay, so now what we need to be able to do is to say, what is the total resistance seen by this battery V2? Well, it's, if any electrons that spin around this circuit are going to go initially going to be looking at charges need to go through the 4K resistor, then they will split. Okay, and that way and that way. If you go left, you get a 4K path back to the negative of the battery. If you go right, you get 3 plus 1, you get another 4K path going back to the bottom of the battery. Okay, so in essence, what we've got is RT, the total resistance seen by the second battery, so let's call it RT double dash, is equal to, we've got 4K, that's the one connected to the positive terminal of the battery, plus, and then we can see a parallel combination of a couple of 4Ks. One goes left and one goes right, but they are effectively in parallel. So we can have 4K times 4K over the sum of those, product over sum again, 4K plus 4K, and as before, it's a similar calculation. We find we have 6 kiloohms. Okay, so then we can say the current I2 double dash, which emerges from that battery, is equal to the battery voltage itself, which is 8 over 6K. And of course, that is going to give us 1.333 or 1.3 recurring milliamps. And then by current division, what we're seeing is 1.3 milliamps flowing in this direction. Splits left and then right. Okay, and so what we do is we say take the supply current to that junction, 1.3 recurring milliamps times the other branch, so the branch that we're not interested in, which is 4K, all over the sum of the two branches, so 4K plus 4K. Okay, which is obviously 4K over 8K. K's cancel, it's going to be a half. And this thing, of course, is going to be equal to IL double dash. Okay, so IL double dash is equal to, well, a half of 1.3 recurring milliamps, which of course is 0.666, etc., 0.6 recurring milliamps. Now superposition says take those two answers which you got. We got IL single dash 4.3 recurring milliamps. Got IL double dash as 0.6 recurring milliamps. We can therefore say finally IL is equal to IL dash plus IL double dash. And I would like, while we're doing this, to indicate IL dash was determined as going downwards, and so was IL double dash, because sometimes in problems one current can go up and another can go down, so you need to be careful on directions. Okay, so the answers to this lot was 4.3 milliamps recurring plus 0.6 milliamps recurring, which of course gives you 5 milliamps exactly. Let's change color, because now we can say the voltage between terminals A and B is equal to I times R. Well, I is 5 milliamps times the resistor value between A and B. That was the 1K resistor. Okay, so we've got 5 milliamps flowing through that 1K resistor. So V equals I times R, 5 milliamps times the 1K. Okay, the milli and the K cancel out. The 5 times the 1 gives you 5, and we end up with 5 volts. Okay, let's see if we can reproduce this result on our simulator. Okay, and we've gone into the microcap simulator here, and we've redrawn that circuit which we just analysed. 52 volt for V1, 8 volts for V2. There's those couple of 4Ks, 3K and a 1K terminals A and B. And all we want to do now really is to determine the currents and the voltages, especially the voltage between A and B, and we're hoping that's going to come out to be 5 volts. And all we need to do, we've got our earth in, which is important. We click on analysis, and then we go for dynamic DC. Little dialog box pops up here, bring it in a little bit, and I can hover over this fourth icon here, which tells us node voltages. Click on that, and hey presto, 5 volts between point A and point B. And point B, of course, is on the earth here. Okay, so that confirms the voltage. Let's take the voltage off. Let's have a look on the next icon, the fifth one, which is currents. And it tells us indeed here we have 5 milliamps flowing from left to right across this path and through that 1K resistor. Okay, so that all confirms our theory. Thanks for watching, and see you in the next video.